Hello, pre-calc. So this is our notes for 11.4, complex numbers in polar form. This is actually something that anyone who's thinking of going into engineering, especially electrical engineering, you will be having to deal with this. Obviously, we're not going to get to that level in this lesson, but just so you know that it does have a foundation there. I remember in college taking a lot of differential equation courses, and we had to deal with complex numbers in polar form. So we're going to do a little bit of review of your imaginary numbers to start off with. Remember that I is called the square root of -1 so that we can work with it because it is naturally occurring, especially in electricity. If I square both sides, you get this nice I squared equals -1. And you can see from the little chart over on the side how it would go. So you get to I to the fourth, and you would actually just get a +1. So it has a cycle of the fourth power. So if I'm simplifying something that has a negative under the radical, you would simplify it the same way you would normally simplify. I'm going to pull out the -1 and then rewrite 48 as rad 16 times rad 3. So the rad 16 comes out as 4. Square root of -1 is I, and the rad 3 stays underneath. So that would simplify. We tend to put the I in between the number and the radical, not at the end, so it doesn't look like it's under the radical. But really it doesn't matter the order you write it. It's just kind of standard. And then if I was going to simplify I to the 27th, what I'm going to do is use my property of exponents and break up 27. I'm going to pull off the highest power of, or factor multiple, I should say, of 4, which would be 24 plus 3 is 27. And I know then I can write that as I to the 24th times I cubed. Well, anything that has a power of 4 is going to simplify to 1 because it's going to be 1 to the 6th power. I to the 4th is 1. And then I cubed, we can then just pull from our list and write that as negative square root of -1. We're not going to be doing too much of that. That's just meant to be kind of a review of your complex numbers. So remember, complex numbers is a combination of you have a real part and you have an imaginary part. And in this particular course, we're going to be calling that complex number Z. So if you were adding complex numbers or subtracting complex numbers, you're just basically adding and subtracting like terms. So what I tend to like to do is I like to distribute my negative. So that negative is going to make this a -2 and the imaginary part a +2i. And then I just line them up and add like terms. So 3 minus 2 is 1. 4i plus 2i is 6i. And that's about as difficult as that gets. All right, you are going to end up having to add and subtract like terms in the process of what we're doing. If I'm multiplying, now you are multiplying two complex numbers, but remember when you're done, anytime you see I squared, you're going to replace that with -1. So I'm going to do my regular FOIL routine, 2 times 6, and then 2 times 4i. So that's 8i. Then I have -3 times 6 is a -18i. I like to write my like terms together. And then I'm going to have a -12 I times I, which is I squared. I squared, remember, is going to get replaced with a -1. So what it always does is it changes the sign of what came before the coefficient there. So I really have here 12 minus 10i plus 12, and I can always combine the first and the last, and that would be your final answer. So when you are multiplying two complex numbers, your answer will always be another complex number. It'll only have the two terms because the middle terms will be combined, and now the first and the last term should be able to be combined as well. All right, now I know you guys have had a little bit of complex numbers in A2A. Oddly enough, no one ever addresses how do you graph it? How do you represent a complex number in a coordinate plane? Well, what they've done is they've made the x-axis the real axis, and they make the y-axis the imaginary axis. So you're still graphing it like you would a regular coordinate where the real is 4, the imaginary is 3i. So to graph 4 plus 3i, I'd go over to 4 on the x, up to 3i, and this would be the coordinate, 4 plus 3i. That would be that dot. If I had to graph negative 2 minus 2i, so I go back negative 2 on the real, down 2i, and this would be the coordinate, negative 2 minus 2i. And that's really as difficult as that gets right now. Okay, now we're going to get into what we want to deal with. So if we put all this into one coordinate system, notice in terms of polar, you have your theta and you have your radius that goes out and it meets up exactly where the complex number, same as when you did your rectangular coordinates. So you have very similar relationships here. We know that, again, b, this distance up here, was r sine theta. We know that a is r cosine theta, and we can now write our complex z. So the x coordinate is r cosine theta. The y coordinate was r sine theta. It now has an I in front of it because it's imaginary. And so we can factor out the r. And so then you have cosine theta plus I sine theta. And because that's a lot, we tend to abbreviate that as r cis theta is how I would say it. Okay, so really what that represents, though, is that. This is just sort of a shortened form. It's kind of like saying SOHCAHTOA represents sine is opposite over hypotenuse, that kind of thing. Okay? All right. Now this next, okay, I'm just going to read this. It's crazy. R is the modulus, which is a fancy name for magnitude or hypotenuse or radius of z. And theta is the argument of z. Well, the argument is always the function you have to figure out in a function. So the sign of x is the argument. In this case, we're using theta because we're talking degrees. Don't worry about the terminology. It's not going to be that important. The absolute value of z, because remember, if we're talking r, your hypotenuse is always positive. So the absolute value of z would be a squared plus b squared, which is your radius. Hopefully that makes sense because that's just Pythagorean theorem to figure out what is r. All right, let's get into how we would actually do this. So that number that we did before, 4 plus 3i, I'm going to go back up. Whoops, I hit the wrong thing. Up to our graph up here, and I'm going to draw the r out to that. So here is the triangle. So we knew that this was 4, this is 3i. By Pythagorean theorem, we know our radius is going to be 5, and what we want to figure out is what is that angle right there. So again, we're trying to convert to polar form, which is r comma theta. By Pythagorean theorem, we know that 4 squared plus 3 squared is going to give us 5. And then to find the angle measure, I can just do my inverse tangent of opposite, except I'm not going to use the I. I'm just going to take the distance, 3 over 4. And in degree mode, again, if it's a degree, round to the nearest full degree. So this would be 5 comma 37 degrees would get me to the same place. that would be your answer in polar form. And again, for the -2, I can come back up here to our diagram. So we did a -2 in that direction, a -2 by Pythagorean theorem, plus it's an isosceles triangle. You should know that this will be 2 rad 2, because it's x rad 2. And since our x is 2, so I know that putting this into our theta, we know that 2 squared plus 2 squared is going to simplify to 2 rad 2. And I really don't need to do any trig here, because you should be able to realize in that third quadrant, theta will equal 225 degrees. But if you didn't know that, you would have to do the inverse tan, and now negatives make a difference. Well, it's going to end up being positive. This would be -2 over -2, which is a +1. Realize that would put you, if you did it on the calculator, which you're not going to have, would put you in the first quadrant, and you'd have to add 180 degrees. So the answer here would be 2 rad 2, 225. So you always want to graph it so you know what quadrant you're ending in to make sure that your theta that you find corresponds. We've already done something like that where you had to, if you land in the second or the third quadrant, you will have to add 180. Okay, so if we want to work with our complex numbers in polar form, I'm not going to go through the derivation, because the derivation is not helpful really for remembering it, and the process is so simple that I'm going to kind of just give you, it's not one of my favorite things, but you can look in the book if you want to figure out the why behind this, or come to Academy and I'll be happy to go through it more. If I am multiplying two complex numbers, like we did before, but we're going to multiply them in polar form, this is what you would do. So I have two z1 and z2. Remember, z1 is going to be like a1 plus b1i. z2 is a2 plus b2i. But if I put that into polar form, so you're going to have r1 cis theta, and you're going to have r2 cis, I should say cis theta 1 and cis theta 2. So if I'm going to multiply it in polar form, what you do is you are going to multiply the r's, since you're multiplying, but add the thetas. All right, and in general, think about logs. Multiplication and addition go together, and subtraction and division go together. So it's kind of the same process. So here's an example. I have 2 cis 154 and 3 cis 27. So if I'm multiplying them, I multiply 2 times 3 cis, and then you're just going to add 154 plus 27. And so our final result is going to be 6 cis 181. That's really as deep as that gets. All right. If I'm finding the reciprocal, which is basically like dividing by 1 of your complex number, and I don't know why we do reciprocal before we do the division, because it actually might make more sense to do division first, but it doesn't matter. So here I'm taking the reciprocal of my converse, so I take the reciprocal of my radius. In general, you're always, whatever you're doing to your complex number, you're doing the same thing to your radius. So I'm going to take this reciprocal, and then I'm just going to take the negative of the angle. And part of that's going to come out when you see what we do with division, because you're not dividing, you're not subtracting from anything else. So here, if I want to find the reciprocal of 2 cis 154, so 1 over z1 would equal, take the reciprocal of the radius, cis negative 154 degrees. Now, a lot of times we will ask you to write the angle in a positive, as a positive angle. So what you would do is just, you could subtract from 360 to figure out the coterminal angle as a positive would be 206 degrees. So just 360 minus 154, that'll give you the 206. All right, so there's one reason why we want to know those coterminal angles. And then lastly down here we have the quotient. So you're dividing the two against each other, and again you're going to divide the radii and now subtract the two. So here's my Z1 and my Z2. So Z1 divided by Z2 is going to be 6 divided by 3 cis, and then 54 minus 67. Again, notice I'm going to get a negative number that I will have to convert if that's what they want is a positive. So this is going to be 2 cis negative, what do I have there? Negative 13 degrees, is that it? Yeah. And if I had to write that as a positive, that would be 2 cis, my brain is not working right now. 360 minus 13 is 347. And that's only if they ask for it in a positive. Sometimes the negative is totally fine. All right, so that's kind of pretty simple. When you're working with multiplying or dividing your complex numbers due to the R, what you're doing to the Z, and then if you're multiplying, you add. If you're dividing, you subtract the two thetas. Now here's where we really want to get into is de Moivre's theorem, which is being able to find either the roots or the power of a complex number. And it sort of follows the same pattern as up above. So what I'm going to also add here is, what if I wanted, so what this is showing is a power, but we in general are going to be looking for the roots. So to find the root, z to the 1 over n, again, whatever you do to z, you do to the same thing to your r, so I would take the root of n. But now, because there's going to be multiple roots actually, what I'm going to do is, so I have n roots. So it's going to be 1 over n, and then that's going to be whatever my theta is. But as I go around the circle, I want to represent all the times that this is going to occur. I guess that doesn't make sense, so we're going to do it as an example. You'll see it's actually really, this is going to be really very easy. So I want to find the cubed root of this example. So I have z equals 8 cis 120. And what I'm looking for is z to the 1/3. Okay, so to start off with, I'm going to take 8 to the 1/3, and I'm just going to work this out in its full entirety this time. Usually it goes a little bit faster. Cis 1/3, my theta was 120 degrees plus multiples of 360, so you fill out your circle. So what would that give me? You will have 3 answers because I'm finding a cubed root. So we're going to start off with, if k is 0, that's going to give me 2 cis, 1/3 of 120 is 40 degrees. And then now 1/3 of 360 is 120 degrees. So all my answers are going to be 120 degrees apart basically. So the next answer, if k is 1, is going to be 2 cis, and what I'm going to do is I'm going to add 120 degrees because you're distributing this. 1/3 of 360 is 120. So 120 plus 40 puts me at 160. And then my next answer is going to be 2 cis, and again, I'm going to add another 120, and that gives me 280. And if I had to graph it, it would look like this. 2 cis 40. Here, I'm going to try and be really fancy, and I don't know if I can do this right. I'm going to make myself a polar graph. Not a bad circle. Okay, So if I was going to graph this, I'm at a radius of 2 at 40 degrees. So that would put me about here. That would be 2 cis 40. Then I have 2 cis 160, which would be about here. And then 2 cis 280 is going to be right here. And so they should all be equally spaced 120 degrees apart. And that's how you find it. Basically, you just find the first one, and then whatever 1/3 of 360, that tells you how many degrees you're going to add to each time. So let's try another one. What if they don't give you the whole thing? So now I'm being given z equals -27, but realize that's also plus 0i. All right? So we want to put this into r cis theta form. So -27 plus 0 degrees is actually a radius of whoops, I lost my pen, is a radius of 27 degrees, cis 180. Now, how did she get that? Because this is a -27, remember. So if I were to graph that, that's -27, and I haven't gone anywhere, plus 0i, that's the y, so this is your -27 right there on the xy coordinate. All right, so what is it they wanted us to find? They want us to find cubed roots again. All right, it's a popular one. All right, so z to the 1/3, and again, we're working off of this, is going to be 27 to the 1/3, cis 1/3 again, theta plus 360k. I don't usually write that first line. I usually go right into it. So 1/3 of 27 is 3. Oh, sorry, that 180 is what I should have filled in here. This is 180 degrees in this particular case. So I should have put that there. All right, so 1/3 of 180 is 60. So again, that's going to be my starting point. That's my first number. And because 1/3 of 360 is 120, I'm going to just keep adding 120 to that. So 120, that's going to give me 180. And then I'm going to have another 120, which is going to give me 300. If I were to add another 120, it would put me again beyond the unit or beyond once around the circle. So let me get rid of this dot for a second, because we're graphing the cubed roots. So again, if I had make my own little polar graph paper. I don't know why I didn't give you polar graph paper. It would have been nice. That wasn't very good, but you'll get the idea. So I'm going to go out to a radius of 3 at 60 degrees. That would be right here. And then 3 cis 180 would be right here. And 300 would be right about here. And again, they should be equally spaced. So if they just give you a part of the complex number, whether it's the real or the imaginary, you fill in the missing part with a 0. And then you can work from there. It's always a good idea to know what the graph would look like if you have to convert it first from the complex to the polar form. So you always want to do it from the polar form. All right, have fun with it.